Hey friends, welcome to Ghosh for AI. My name is Sharnand Ghosh, and here we have been talking about machine learning algorithms that are absolutely necessary before jumping on to complicated tasks like deep learning. This is the last video of this 5-part series. If you haven't seen the other videos, I will post a link to the description, link to the playlist in the description below. Please go ahead and check it out. We have been talking about KNN classification algorithms and k-means clustering algorithms. We also talked about more complicated stuffs like support vector machines and neural networks in general. But now we have come across this thing called principal component analysis, which is a dimensional reduction technique. Now this technique is very famous in the machine learning community. It's one of the prime things that are taught in any beginner level machine learning course. And the beauty of this thing has been invented a long time back, and it is one of the earliest attempts at an automatic feature extraction technique. Now, principal component analysis, what it does, it reduces the dimensions that we need for representing a sample. Now, why do we need to do that? So we have something called the curse of dimensionality. Now, what it does is, say we have a one-dimensional representation of our sample, and basically, if we consider the range of values that the sample can have in that one dimension, then we can create 4 different regions in which those values can occur. And say we have assigned meanings to every one of those regions. Now, if we think a similar kind of separation in 2 dimensions, we'll end up having 16 regions in which the samples can have a different meaning. That is 4 regions along one axis and 4 regions along the other axis, and it's a total of 16 different regions. So as we keep on increasing the dimension, so if we add a third dimension, it becomes 4 cube, that is 64 dimensions. And from here we can understand, or we can guess, that as we keep on increasing the dimension, the number of regions that can have meaning, it increases at an exponential rate. That is, the sample has an exponentially more region to occur in. And hence any good machine learning algorithm should attempt to use as much less amount of features as possible, because not only is it more effective to build your algorithms, but it's also a much more smarter representation of your sample space. Here algorithms like PCA thrives and really has proved its worth for problems like this where you have to reduce the dimensionality. Some other algorithms that does a similar thing is, you can say, singular value decomposition, or say linear discriminant analysis and things like that. Now, what does PCA do basically? So say we have this representation of our data or sample points in these 2 dimensions, that is the x-axis and the y-axis, and we want to convert this convert this sample space into a different space where we have a lower number of dimensions. Say from 2-dimensional representation, we want to map them into a single dimensional representation format. So in a single dimensional representation format, we'll have only one axis. So if we draw an axis and if we map these samples onto that axis, like if we draw perpendicular from the samples onto that axis, then we can get a different representation of the sample points in this new axis that we have just created. Now, can we just create an arbitrary axis like this, and can we just map the samples onto that axis and use them? Of course we can. It's not that we can't use them, but the thing is, will it be effective enough? Now, what do we actually desire when we are doing this kind of mapping from one dimensional space, or rather from 2-dimensional space to a single dimensional space? What do we really desire? What we desire is that these samples are very much separated, or as separated as possible in this new dimension. The reason is that because if they are more separated, it's much easier to draw that straight line between them. If the samples are very much clustered together, then it's much harder to draw the straight line to separate these samples according to our need. And hence we are looking for that line in which these mapped samples will have the maximum separation. And in terms of statistics, what we have is we have the variance speaks of how separate or how far away are the samples from their mid position or from their mean position. So our goal is to choose a new axis such that the variance of the mapped sample points is the largest. Alternatively, we can also say that these perpendicular distances, it has to be minimal, like the samples themselves has to be as near as possible to our to our new axis or new dimension. If even if we try to do that, it kind of means the same thing. And you can finally understand that if we solve this problem, if we maximize the variance, what we end up having is a straight line like this. And here we can see that there is the separation among these red points are the maximum, and no matter wherever we change this line or however we rotate this line, we'll be getting a worse distribution of samples as compared to this one. Now, mathematically speaking, what does this represent? If you see, I have drawn an ellipse over the data distribution. Now, what this signify is, this ellipse is kind of an approximation of the distribution of the data samples in this space, and the green line is kind of the major axis of that ellipse. In terms of discrete mathematics, or if we represent these samples in a matrix, what it means is this green line is the eigenvector corresponding to the highest eigenvalue of that matrix. So as I have written here, U is the eigenvector corresponding to the largest eigenvalue of the matrix representation of these data points. And this eigenvector gives me the most ideal direction of the new dimension where the variance among the data points will be maximum. And that's simply PCA for you. It can be scaled up to a large scale of problems, large amount of problems, even problems where we deal with thousands of dimensions. We can use PCA to reduce the number of dimensions and kind of grab the principal components, like a finite number of principal components, to create a new dimensional representation, so that we can work with we can use them in other machine learning algorithms in a much more efficient manner. So I think this is the end part of in the slide, but I'll be taking you to one demo, online demo as well, where we can see some real life things in action. But before that, please go and study these papers called the principal component analysis. It like lists some of the nice applications of principal component analysis in the field of machine learning. Also, you can go and try these blogs. You have scikit-learn, MATLAB, and again Weka for applying this kind of algorithms. There are nice functions available. Now let us go to the demo where we can visualize how this principal component analysis works. Okay, so this is a very nice website where it gives us some a 2-dimensional, 3-dimensional, and a 17-dimensional example of how this principal component analysis works. So we have a 2-dimensional representation. This is an editable format. What it does is we can just change these points, and it will give me a representation of our principal component. So this red line is our first principal component, that is, it's the axis corresponding to the largest eigenvalue, and this green line is our second principal component, that is the axis corresponding to the second largest value. Now we can see that if we say line up these samples in like a ellipse format, you have the red line which is parallel to the major axis of the ellipse that fits over these data samples. If you can visualize it, it's the major axis of the kind of this ellipse. Now what is, if we map these samples in our new sample space where PC1 and PC2 are the axis, the data distribution, it looks something like this. Now if you can see, the data distribution has maximum variance across the first principal component and the second maximum variance across the second principal component. So if we move the samples again, if you see, the red line again corresponds to the maximum or the major axis of the ellipse, and the data distribution is again in a way such that the variance along the PC1 dimension is maximum. You can also see the how these values are mapped. So okay, so if you see, we have 5 points here. In the y-axis you can see only 4 points because these 2 points overlap to the same y value, and in the kind of say in the x-axis also there is a very little separation among these two. When we are drawing the principal component, you'll see that the first principal component is drawn in a way such that there is maximum separation among the points, and the second principal component has the second maximum separation among the points. No matter how we change the samples, it will always follow this trend where there is a maximum distance between the samples in the first principal component and the second maximum in the second principal component. And okay, so I think that's it for the two-dimensional case. In the three-dimensional case, it's not an editable version, but it's still significant in some way. So what we have here, if you can visualize that there are 3 clusters of values in the this representational space. Now in this XYZ space, you can see that the values are make a very fuzzy line, and they are not, these groups are not very apparent in this X, Y and Z dimensional representation of the data. But if we consider the PCA version, like if we draw the PCA in a way so that this red line is across the major axis of the ellipse that fits over all these data samples. So we have shown the PCA. If you see, the red line now goes through the direction in which the major axis is supposed to lie if we draw the ellipse. And now you see in the first principal component we can have 3 different clusters of the data samples in a very well distinguished manner, and this is what makes PCA so attractive. Not only does it reduces the number of features, so we had 3 features in XYZ, and now we can even ignore PC2 and PC3 and work only with PC1, and even then we can draw a straight line to separate these two, separate the groups together using only one dimension. So this is how the PCA performs so well, because due to the maximum kind of separation in the first principal component, it is easy to draw the hyperplanes in that axis itself. And here we have a even larger example where you have a 17 dimensional example, and they have not shown the mathematics that goes on in the behind, but they have shown one result that they have obtained, that in the first principal component it is seen that Wales, England and Scotland are grouped together and Northern Ireland is grouped differently. Now now this can look like okay, maybe the data distribution is in such a way that the Northern Ireland is different than these 3 things, but the thing is, even if you see in terms of real world, Wales, England and Scotland are the 3 islands of the Great Britain, and Northern Ireland doesn't actually belong to the the 3 islands of the Great Britain, and hence because of this geographical separation there is also a distinction in terms of the kind of things that they consume. So alcoholic drinks, okay, England, Scotland and Wales have much more consumption of alcoholic drinks as compared to Northern Ireland, and same is true for many other samples. But just by seeing these 17 dimensions, it's not so easy to really understand or really grasp how this what these things mean, or what is the significance of this data distribution. But when we draw the principal component, in the first principal component we can clearly see that the geography of the region plays an important role, and Wales, England, Scotland end up in one place and Northern Ireland ends up in another place, and thus it's a very good clustering because the data sample is a good significance of the actual real world geographical distribution of the locations as well. So with this, I guess this is the end of the PCA chapter and also the end of this series of 5-part videos. I really hope that you liked this video, and please share this video with other people or other friends that you're working with. I hope this helps. Okay, so I'll be giving a link to the presentation that I'm using in the description below. If you liked the video, give me a like, or if you didn't like, give me a thumbs down and tell me how I can improve this video. And also tell me about what kind of things you expect from me. Or if you have any questions, ask me in the comments below. I will try my best to answer them to the best of my knowledge. And subscribe for getting more updates in the future. And don't forget to click the bell icon for notifications. See you and have a very good day. And thank you for watching.